Alright folks, good news. Last video for this optics unit, at least for a while. This is going to be a thin lens equation example. Here we're going to deal with what it looks like when we have a concave lens. Remember, a concave lens is a diverging lens. So when the light comes in, it all spreads out, which means we have to trace back to find the focal point. So the focal point's on the side of the lens that we don't usually expect it to be. And the way we handle that mathematically is we make that focal point negative. That negative you can think of as representing a virtual focal point, or you can think of as the fact that the focal point is on the negative side of the lens for focal points. Anyway, the equation here, 1 on di plus, or 1 on do plus 1 on di, 1 on the distance to the object plus 1 on the distance to the image is equal to 1 on the distance to the focal point. The object is 10 centimeters away from the concave lens, so 1 on 10 centimeters plus, we're determining the size and location, so we don't know the location, 1 on di is equal to 1 on the focal point, and here we use our negative, so it's 1 on negative 5 centimeters. Again, easy to convert to decimal places here, so we might as well. 0.1 centimeters to the negative 1 plus our unknown image distance, and then 1 on negative 5, which works out to be negative 0.2 centimeters. Now, subtracting 0.1 centimeters from both sides to get 1 on di on its own, I get negative 0.2 centimeters to the negative 1. Minus 0.1 centimeters to the negative 1, which works out to be negative 0.3 centimeters to the negative 1. Taking the reciprocal of both sides, or flipping both sides, I got 3.33 centimeters negative. Now, with all that in hand, I can figure out how big my image is using my magnification formula, the height of my image divided by the height of my object, and that's going to be related to my image distance and my object distance. Negative, right? So, the height of my image, I don't know. That's an h. I gave myself one more 5 centimeter tall object here, just to, doesn't matter. Anyways, I have a negative image distance of 3.33 centimeters, and that's being divided by my object distance, which was 10 centimeters. So my magnification here is going to be quite low, or I'm going to make this thing smaller. I'm going to make it 0.333, I could keep going anyway, of its original size, or essentially a third of its original size, which means my new image is going to be, let's say, 1.67 centimeters tall in comparison to the 5 that it was originally. So my size is 1.67 centimeters tall. My attitude, since this is a positive, those two negatives canceled out. Oops. Those two negatives canceled out. This is upright. The location is 3.33 centimeters. The negative here means that it's in my, if this is my lens, remember this is the positive side for images. So the negative here means that I'm on the wrong side, or I'm to the left of the lens. And my type is virtual. Quickly, I'll just show you what this looks like from the ray diagram perspective. Here, I said that my object is 10 centimeters in front. And because I'm dealing with a diverging mirror, what did I say the focal point of that was? 5 centimeters? With a focal point here of 5 centimeters, remember that's the forwards one for this kind of one. And I have backwards, which would be about here. So the forwards ray goes parallel and then deflects in line with that focal point, so that's going to diverge like that. And then the secondary ray is headed towards that virtual focal point when it hits the lens and goes parallel. If I extend both of those rays back, because they're not going to meet out here, they're diverging, then I get a little image here, and we can see that that image is small, it's upright, it's to the left, and it's virtual. So that is how it works for a concave lens, and there's only really one case for the concave lens. They all sort of work out the same way.